Okay, so we can graph these relationships. So we were just looking at sodium, which is here, and chlorine, which is here. The energy required to remove an electron is on the y-axis, where energy is increasing from the bottom to the top. So sodium has a lower energy, and chlorine has higher energy. All of these elements are in period 2. No, that's incorrect. They're in period 3. All of these elements are in period 2. Lithium is on the far left of period 2, and neon is on the far right. So, if we wanted to sketch this relationship, we have lithium on this side, it's got low, and we have neon on this side, and it's very high energy to ionize it. So, you can draw your arrow like that. Now, if we compare in the same group, say we look at helium, we'll look at the noble gases just for fun. Okay, we're going to do it in purple. So helium versus neon versus argon versus krypton. The trend is kind of increasing this way. So krypton would be down here, and helium is up here. So we would increase ionization energy pointing towards helium. So helium has the highest ionization energy of any atom on the periodic table. Okay, so let's summarize. Metallic character points towards francium, non-metallic goes towards helium. Atomic mass, what's the biggest element in the periodic table? Francium. And the smallest in the periodic table is helium. So our atomic radius arrows get biggest pointing towards the bottom left. Ionization energy, we just figured out. Sodium compared to chlorine. Sodium has a much lower ionization energy. So going across the periodic table, it goes from low on the left to high on the right. And then we looked at helium compared to krypton, and we said helium is the highest one, so we're going to point our ionization energy arrows towards helium. That means the lowest energy ionization is francium. So what we know about francium now is that it is the biggest atom, it is the most metallic atom, and it is the lowest ionization energy on the periodic table. Helium, on the other hand, is the highest ionization energy, the most non-metallic character, and the smallest radius. Okay, so when things ionize, they change size. If I get rid of a bunch of stuff from my house, I have way more space. So the same thing kind of works here. If we kick out an electron, we shrink. When we absorb electrons, we're bringing electrons into the atom, you get bigger. That makes sense because you're adding layers to your shapes, right? So cations have a positive charge. Remember this. Cations are positive. Get it? Like a cat. Cat paws. Yeah, it's genius, I know. So cations are positive. So anything with a positive charge is a cation, like lithium. And in order to have become a cation, it had to give up electrons. So, when we give up electrons, we shrink. So it went from a radius of 1.28 to a radius of 0.90. So they get smaller. On the other hand, nonmetals are really good at taking electrons. So like if we look at oxygen, let's say, let's look at sulfur. Sulfur starts out at 1.05, and then it takes 2 electrons and becomes 1.70. Since anions are negative charges, meaning they absorbed electrons, they must get bigger when that happens. We can quantify how much a particular element likes electrons or doesn't. We said that sodium really likes to give up its electrons. That means it's not very good at absorbing them, so it has a low electronegativity of 0.9. Chlorine, on the other hand, has a very high electronegativity of 3.0. Okay, so the bigger this number, which ranges anywhere from 0 to 4, the 4 is the the most electronegative, and that's fluorine. The bigger the number, the more electronegative it is, which means the more it loves electrons. It steals them from anywhere it can get. So fluorine is the ultimate electron hoarder. Okay. Now, this is useful because I can actually calculate the electronegativity difference, and it will tell me whether my particular molecule is covalent or ionic. So covalent bonds are when electrons are shared. It means the electrons don't transfer from one to the other. This is usually between two non-metal atoms, say carbon and oxygen and carbon monoxide, or even carbon and oxygen and carbon dioxide. That's two non-metals, carbon and oxygen, and so they share electrons. An ionic bond is different because the electrons are not shared, they're completely transferred. This is similar to what we saw when we made sodium chloride. You get an Na plus and a Cl minus. They do not share at all. The electron has moved over completely. Okay? So we can use electronegativity differences to figure out which kind of bond we have. So here's a nice diagram. This doesn't exist in your textbook or anything. It's just in the notes. You may want to print this because it's a nice reference. So if I have nitrogen, this is what it looks like. It's two blue spheres that are sort of attached to each other. And I look on this electronegativity table for nitrogen, and it says the value of nitrogen is 3. Well, I have two N's here, so it would be 3 minus 3 because they're both the same atom. And so the difference between them, that means to subtract, is 0. Anything that has an electronegativity difference of 0 we call nonpolar covalent. Anything that's bigger than 0 but less than 2 we call polar covalent. So for example, oxygen and hydrogen in the water bond. Oxygen has a value of 3.5 from the electronegativity table, and hydrogen's about 2.1. So it falls in the range of polar covalent. If I reacted sodium and fluorine together, fluorine has a value of 4.0, sodium is 0.9. The difference between them is 3.1. So anything bigger than about 2 all the way up to 4 is ionic. Okay. Only things that are exactly 0 are called nonpolar covalent. Anything in between those ranges is called polar covalent. Okay, so let's practice. We have carbon and hydrogen, and if we go back and look at our table here, I want to get carbon's number here is 2.5 and hydrogen is 2.1. So we're going to go 2.5 minus 2.1, 0.4. So this would be a polar covalent because it's bigger than 0, smaller than 2. Our next one is carbon and oxygen. So let's go back here. Carbon is still 2.5 and oxygen is 3.5. So I'm going to take the big one minus the little one. You get 1. So that is also a polar covalent bond. Na and Cl. Okay, so we got Na is 0.9, Cl is 3.0. So 3.0 minus 0.9 gives us 2.1. So this one would be ionic because it's bigger than 2. Our cutoff here is 2. And strontium with fluorine. It's the wrong way. Strontium is right here. It's 1.0. Fluorine is 4. So to be 4 minus 1 is 3. So this is also ionic. Okay, so last review. So far, most metallic element in the periodic table is francium. So metallic character points to francium. The least metallic is helium. The biggest atom in the periodic table is francium, and the smallest one is helium. Our ionization energy is biggest for helium, smallest for francium. So our arrows point the opposite direction from atomic radius. So what's interesting to note is the bigger the atom is, the easier it is to ionize. The bigger the atom is, the lower the ionization energy is. So that's good to know. Now, looking at the trend for our table over here, we see that, like, comparing, say, lithium at 1.0 to fluorine at 4.0, we get bigger going from the left to the right. So left to right is bigger. So it kind of follows the ionization energy trend. And as it turns out, it does that for the vertical axis as well. So in other words, something that is easy to ionize does not like electrons. So that makes sense. It's trying to get rid of the electrons. Helium really likes electrons, so it has a very high ionization energy. And if it were on our electronegativity table, which it isn't, it would have a very high electronegativity. We usually don't put the noble gases on the electronegativity table because they are so attracted to electrons that it's ridiculous. Plus, they don't make compounds anyway, and we mostly use electronegativity to compare two atoms connecting to each other. So it mostly, if somebody asked me to tell them what the most electronegative atom in the periodic table is, I would probably say fluorine, because helium doesn't react, so we don't usually plot it on there. Okay, that's it for Chapter 5. There's a few questions in Top Hat you'll need to answer, and then there will be a quiz on Blackboard that is due by next Monday. Oh, and as always, feel free to contact me with any questions.